Now, we can start to talk about angular momentum. Okay. Angular momentum is a quantity can be compared with linear momentum. Okay, so for all this to describe the rotation, we can introduce all these quantities in the way we did before for the translation. So for the translation, we have the force. So here we have the torque, we have the mass, and then we have the rotational inertia. And so we have the angular momentum, the linear momentum P, and here we have the angular momentum L. Okay, so there are some one-to-one correspondence between the description of the linear motion and the angular motion. The angular momentum, we use L to denote it. Now let's look at the definition of the angular momentum. Okay, the general definition is L equals to R cross P. Okay, so meaning of the angular momentum is involved with the cross product. Okay, so like torque equals to R cross F, and this one equals to R cross P. And again, you can see some pattern here, right? This is R cross its counterpart, F. This is R cross its own counterpart, linear momentum. Okay, so of course, with the cross product, you can further expand it in different way. Since P equals to M multiplied by V, right? So this is R cross M V. And M is a scalar. So you can factor it out before the cross product. So you get M multiplied by R cross V. Okay, so you can write it in many different ways. But in any expression, it's R cross another quantity. Okay, R should be the first quantity, because we know that for the cross product, A cross B is different with B cross A. So the order here is something you have to make sure you're clear. Okay. And this is a vector notation. So if you write in this way, it can tell you both the magnitude and the direction. The direction is given by the right-hand rule, right? If this is the direction of the R, this is the direction of the P, the momentum or the velocity. So you make your hand, in a way you can put your finger from the direction of R to the direction of velocity. And this direction is the direction of the angular momentum. Again, the direction of the vector, angular momentum vector, you can see is actually perpendicular to the rotation of the plane, right? If the rotation is along the plane of the table, then the direction of the angular momentum is either upward or downward. Okay, so that's the definition of this kind of so-called pseudo vector. The direction of the vector for those rotational quantity is actually perpendicular to the plane of the rotation. Okay. Now for the magnitude, we know A cross B. The magnitude of A cross B equals to AB sine theta. So of course, the magnitude of the angular momentum, usually if we don't put an arrow sign, that means that magnitude, so it can be written again in different way. Okay, what we given there, FVR sine theta mv is p. So that's p multiplied by r multiplied by sine theta. Theta is the angle between the momentum direction and the radius direction. And of course, just similar to this one, you can try to write it in a way like p, the momentum, multiplied by r perpendicular, or mv multiplied by r perpendicular. Okay. And to determine the r perpendicular, you use the same stuff you learned for the talk. Okay. How can we find out the r perpendicular? So if, like, say, the velocity or the momentum is in this direction, and r is in this direction, this is r, okay. And then if this is center, this is p, and this is r perpendicular, right? So you have to make a line perpendicular to the direction of the momentum. Okay. And this one is r, the distance perpendicular to the direction of the force. This one is r perpendicular is perpendicular to momentum. Okay. Another expression is that all these expressions are useful when you consider the circular motion for some mass particle. Okay, if you know the radius and you know the velocity, it's easier to use one of these expressions here. But if you have the rotation for the rigid body about any point, like about this point, if the object is in rotation like that, it's easier to use L equals to I omega to calculate the rotational inertia. Okay? And you can see, we can check that these two kind of expressions are actually the same. For example, if it's some mass particle with r mass m and the radius r here, if it's in some rotation, let's try to calculate the angular momentum from this. Then L equals to, for one mass particle, the rotational inertia is simply m r squared, right? And multiplied by omega. But on the other hand, r multiplied by omega is velocity, tangential velocity v. So this equals to m r v. Okay. So on the other hand, if it's in the rotation, so the velocity is along tangential velocity. So r is actually the same as r perpendicular. So this is m r perpendicular v. Same as this one. Okay. But of course, for extended body, then you have to use this one. For mass particle, you can use this one or start with this one to derive this. Okay, do you have any question here?